resolution calibration. Okay. To me, it never makes sense to run mass without resolution, so I run them all at once. Okay.
We always fill or no, we always fill sample.
Oh.
We never use them, but we always fill.
What is your zoom target? Oh, only 1,000. Let's put up at 3,000.
We never use it, so I don't care.
Well, I want you to pass it. I want to feel like I know what I'm. That your instrument's really. If not, eventually I want to get you an engineer to fix it. So now it's going to go find the 5 masses and make sure it can see them properly. Okay. And what I wanted to do is I keep an eye on this just to make sure. Remember how I had that little junk peak? It didn't grab it. Okay. So now the right.
So you memorize all these masses and you know what.
That's, you know what that is? That's a loserville. I can actually draw you the full MS2 of angiotensin and label all the peaks properly. With the abundances I typically see on a trap, yes. The 784, the 1028, the 630, I got them all down.
Scott Vaccaro in San Diego used to be able to just look at the tandem messes that come out and say the phosphopeptides that they were.
That's loserville.
You'd be like CD3 receptor, bam, bam.
Now, what it's doing here is it's varying the ejection amplitude is the resonance ejection. This is the kicking of the ions out via the dipolar. It's trying to find out what voltage gives me the narrowest peak. Okay? And it's going to do that for each mass. All of these tests are purely empirical. Okay? We know what voltage we need to adjust, and we adjust it till we get the smallest number. Smallest peak with the... Now, this is doing rough mass calibration. So this is... It was plotting mass over charge versus quadrupolar RF. Okay? And it's measuring how well it did. Okay? Nope, it was varying the voltage of the quadrupolar to move them to the right frequencies.
The
dipolar was resolution, quadrupolar was mass. Okay? Because the dipolar, if we kick the ions out without the right voltage, okay, we end up with weird peak widths. They kind of scatter and do some weird stuff. Okay? The quadrupolar is, you know, which voltage brings it up to the proper frequency at the right time. It just calibrated your AGC for you, which is 5 times faster scan rate. And it only had to be a rough mass accuracy. Now it's doing your zoom scan. Okay? So this zoom scan is 16 times slower. So normal scan is 16,000 AMU per second. Zoom scan is 1,100. By slowing the ejection of the ions out of the trap, we can get more data points and we can resolve the peaks better. Okay? And we do the same thing. We find out what resonance ejection voltage best ejects that mass. So we're doing dipolar voltage versus peak width, and we're trying to find the minimum. Okay? The tests are always the same. We start off with resolution. What resonance ejection, what dipolar voltage gets the shortest peak width. And then we do mass calibration. What quadrupolar voltage brings it in resonance at the correct time, gets the right frequency. Okay. Now it's measuring them. And it's going to do a mass calibration. So this is quadrupolar RF versus M over Z. Now it's measuring how well it did. Your resolution of your 1822 peak was too low. You failed zoom scan. Is that what you usually get?
We always
We can look at that one later. That might be. Especially, I put it in glass too, and so you can get rid of that goobers at 1800. Now let's do an ultra zoom scan. Does it pass this or fail this?
Ultra zoom, it always passes. But the zoom, it always passes.
And it's doing the same thing. It's doing resonance ejection voltage versus peak width.
And what's the AMU per second on ultra zoom?
28. So this is substantially slower.
And this, it's actually only acquiring data in a very small range of mass.
Right.
That's the full thing that it's actually acquiring.
Right.
With an FT, all these things are sort of, so.
Yeah. The key is, with the ion trap, we can get as much resolution as we want. We can get 1,000,000 resolution. We still never get the mass accuracy, is our problem. Okay. Our ultra zoom scans are thinner than hell, but they're still not at the right position. Okay, you'll notice he's off by almost 0.3, 0.4 m over z.
With the FT, you get the resolution across a large.
Right. Correct.
Very quickly relative. If you would try to sample across here with ultra.
Yeah, that would be slow.
So it appears that the charge street screening is not working.
Yeah, I talked to Eric, the other instructor. He was just at Wistar with the spikers. He goes, it didn't work for them either. So we're trying to collect it.
Advantages of having.
I want to see if I can get a data set of yours, if you don't mind,
Sure, I'd love to help you
and see, convince Brayman that the code doesn't work.
If the peaks are really low abundance and there's no charge state distribution.
Yeah, it should have skipped those.
But then if it were to skip them, we'd miss that phosphor optimize.
See, for you, I wouldn't use it because the stuff you go after blows my mind.
Yeah, we did some control experiments.
I would love to see the data to see what the charge screening actually accomplished.
Yeah, I didn't really dig for it. It could have just been fluctuations.
Yeah.
They seem to be consistent through multiple runs. Always found more possible compounds. These things are so hard to really see if you made a difference. You know?
Yeah.
Usually we use a readout how many phosphorylation sets you discovered, because that's all we really care about. It's somewhat laborious to get that number. Does ultrasound use the 1822?
No.
So maybe that's it.
Yeah, I can fudge zoom scan not to use 1822.
Yeah.
But it's still kind of, I feel like I'm cheating.
Cheating. We don't care.
Okay, so I'm going to uncheck and always scroll all the way up because occasionally bugs will check other things off and you don't want to repeat something you already passed. So we're going to do isolation and activation. These are the frequencies. Okay, right now we haven't touched any of the frequency stuff yet. We've just touched voltages. So now we're going to adjust frequencies of the Q value. Okay, right now we assume the Q value plot was correct. Now we're going to actually measure those frequencies and make sure they're correct, and if they're off, we're going to adjust them. So isolation and activation are all about the frequencies. And see what we're doing? We're looking at a mass, and we're adjusting the Q value, and we're trying to find exactly where the mass is really sitting on that picture. Okay. We do it at gross.
Of ion instability, the signal will drop out here.
Right. Right. What we do is we put the ions in the trap, okay, and then we adjust the frequency on the dipolar, and the minute the frequency is correct, the ions get kicked out, and we get a signal.
Because you're detecting the reaction.
Right. Okay.
Wow.
So we do that at a gross level, and then we fine tune it. What?
What's Q?
Q is the calculated number that relates M over Z versus voltage on the quadrupolar. And then remember we make that stability diagram, we plot Q versus A, and we put the masses on. And then we bring the masses over to the ejection point.
So this step to check the mass accuracy.
Not mass accuracy.
It's a Q.
Frequency accuracy. Okay, what we want to know is when we want to isolate that ion. Okay.
Is the Q the same for every mass?
What?
Is the Q keep the same for every different mass?
The Q of ejection? Yes. The Q of ejection is always